Hello, everyone. I'm Dongmei Zhang from Microsoft Research Asia. Very glad to have this opportunity today to share with you our research on cloud intelligence, infusing AI into cloud computing systems. I'll first talk about the motivation of our work. Then, I will introduce the concept of cloud intelligence and its research landscape, followed by 2 example projects. I'll share our learnings and future research opportunities at the end. When talking about the motivation of our work, let's take a moment to look at what was happening in the software industry in the past 10 to 15 years. One significant paradigm shift was the migration to cloud computing. More and more businesses in different industries have realized the benefits to migrate to the cloud in the era of digital transformation. Businesses need to collect huge amounts of data, store the data, process the data, get insights from the data, and use the insights to take actions to improve their existing businesses, as well as create new business opportunities. They need to do all of these at scale with low cost and high agility. They cannot afford to use the traditional IT approach to achieve this, especially for small and medium businesses. Therefore, cloud computing would be a natural choice for them. Gartner's prediction also supports the migration to cloud computing. The table on the left shows the percentage of cloud shift in the next few years after 2018 for different types of software. The table on the right shows the predicted market value for different types of cloud services from 2019 to 22. COVID-19 accelerated the migration to the cloud. The implication of this is profound. It means that cloud computing platform is becoming part of the basic infrastructure of our society. The non-functional properties of cloud computing systems would become immensely important, including availability, reliability, performance, security, etc. As researchers in the industry research lab, we have experienced the impact of the trend of cloud computing. On one hand, Azure is one of Microsoft's big bets. It has massive scale with more than 60 regions in the world and millions of physical machines. On the other hand, cloud computing and the digital transformation it enabled got us to think about digital transformation and software industry. On the surface, the question might seem odd since software is naturally digital, but deep down, the question is really about how we develop software, operate software systems, and engage with customers. We realize that software analytics, the interdisciplinary research direction we proposed in 2009 that utilizes the data-driven approach to address various challenges in the software domain, is the digital transformation of the software industry itself. Given the paradigm shift to cloud computing, we focus our software analytics research on cloud computing. We call this new topic cloud intelligence. Cloud intelligence is to utilize AI and ML technologies to design, build, and operate complex cloud services at scale. Centered around 3 key elements in cloud computing: service, customer, and engineering. Cloud intelligence has 3 major topics: AI for system, AI for DevOps, and AI for customer. The North Star of cloud intelligence is for cloud services to have built-in intelligence, meaning they should monitor themselves, analyze, and assess the status, and they should be capable of self-adjusting and adapting to new conditions. Of course, there will be developers and operators in the loop when needed. With such intelligence, when dealing with service issues, the services will be proactive instead of reactive in order to minimize customer impact. Working with our colleagues at Microsoft, we have been promoting the research and practice of cloud intelligence, both inside and outside Microsoft. We initiated the Cloud Intelligence Workshop series in research communities with steering committee members from both academia and industry. The first workshop was at AAAI 2020, and the second workshop was at ICSI this year. With this effort, we hope to create a forum for researchers and practitioners from AI, software engineering, and system communities to work together on this exciting interdisciplinary research topic. In recent years, AIOps has become a very popular word. It was first coined by Gartner in 2017 to refer to the application of machine learning and data science to IT operation problems. Compared to cloud intelligence, Gartner's AIOps concept focuses only on DevOps, whereas cloud intelligence has a much broader scope, including AI for system and AI for customer. We would like to extend the scope of AIOps to make it exchangeable with cloud intelligence. Now let's look at the scenarios of cloud intelligence. For services, the scenarios are around service health, specifically how to measure service health that spans multiple aspects, including availability, reliability, performance, security, etc. Using various metrics of components and resources, how to detect anomalous behaviors that may lead to service health problems. Furthermore, instead of passive response, can we predict service problems before they occur so that we can take proactive actions? And what actions can we recommend? For engineering, all the scenarios are familiar, but many of them may present new challenges in the context of cloud computing. For example, incident triage is more complex than bug triage because incidents are unplanned service interruptions or service outages. Since online service systems are highly complex, one incident may lead to another and many others, meaning although these incidents are reported by different monitors, they are all related and share the same root cause. In this case, the traditional bug triage techniques may not be sufficient to triage incidents. For customers, let's look at intelligent customer support. To cut down cost and improve efficiency, how can we enable self-service for customers? How can we provide actionable suggestions to customers? When a customer does talk to a service support personnel, how can we help make the communication easier and efficient? The scenarios of cloud intelligence are quite broad. We may find more when we go deep into the space. When we explore the scenarios of cloud intelligence, we find that 4 major problem categories can be extracted out across different scenarios, namely detection, diagnosis, prediction, and optimization. Each problem has its own challenges. Let's take detection as an example. To ensure service health, at runtime, it is important to continuously monitor various metrics and detect anomalies in a timely manner. In the development process, for example, when we are doing continuous integration and continuous deployment, we should have mechanisms to catch the defective builds in order to prevent them from being deployed to more production sites. Both scenarios require timely detection. Furthermore, in both cases, there are common challenges for conducting effective detection. For example, time series data and log data are the most common data forms, and they are often multidimensional. The data may be noisy, and there may be different requirements on the detection, etc. On the right-hand side, I'm listing some of our work in the past few years trying to tackle some of the challenges in cloud intelligence. Next, I'll use 2 example projects to show what we have done. The first project is disk failure prediction. Availability is a critical issue for cloud computing platforms, and hardware issues are one of the top reasons that cause VM to go down and reboot. As our partners in Azure found, disk problems are the most severe one among hardware issues. A typical cloud system like Azure uses hundreds of millions of disks, making disk-related problems a top priority to address. To reduce VM downtime, it is not enough to replace disks after they fail. We must take actions before disks fail, which requires us to do prediction. In general, disk failure prediction can be formulated into a binary classification problem. Given a time series collection of disk attributes, predict whether a disk will fail or not after a certain period of time. There are three key challenges in solving this problem: what features to use, what model to use, and how to address the huge data imbalance problem. A lot of research has been done on this problem in the past 10 years. Here are some representative ones. Based on their underlying machine learning models, these works fall into two categories. One uses the traditional machine learning models, such as SVM, decision tree, and random forest. The other uses deep learning-based approaches, such as RNN and LSTM. I'd like to share some of our observations when working on disk failure prediction. The first observation is that, in general, disks exhibit errors before they completely fail. Based on our statistics, on average, disk errors occur about 16 days earlier than complete disk failures. Disk errors, such as latency errors, timeout, and sector errors, are often reflected by the system-level signals, such as OS events, recording symptoms such as file open errors, VM not responding to communication requests, etc. This observation helps us address the problem of what feature to use. Most of the existing approaches only use the smart data that monitor the internal attributes of individual disks. In our work, in addition to smart data, we also use system-level signals such as OS events, as shown in the table. Besides, driver-related attributes such as flush count and controller reset are another useful source. The second observation is that each individual disk is not independent. Instead, it has neighbors because a set of disks can be in the same storage array, or they can be associated with the same server managing data access, or they can be associated with the same computing node, etc. This implies that the health status of a disk may be related to the health status of its neighbors. Based on this observation, we designed a neighborhood-aware component. As shown here, for each disk AI, we represent its status using a vector Ri called neighbor-encoded vector. Ri encodes the status of AI and all its neighbors. It is used as input to the next component of NTAM. Our third observation is that if a disk fails at time t, then there exists a leading time L that the disk samples collected between t minus L and t carry information indicating the upcoming failure. So we mark these samples failure samples, which effectively addresses the huge challenge of imbalanced data, which can be as low as 3 to 10,000. We call this data enhancement method TPS, which stands for temporal progressive sampling. The leading time L is treated as a hyperparameter in the model. Here's an overview of our proposed Neighborhood-Temporal Attention Model, NTAM. It is an end-to-end deep learning-based approach. It has three components: the neighborhood-aware component we just introduced, the temporal component that also leverages the attention mechanism to better capture the temporal information, and the decision component that determines the failure probability of a disk. We evaluated NTAM against 10 state-of-the-art baselines on 2 industry datasets and 1 public dataset. NTAM achieved the best performance in all the evaluations. This is the result on the industry datasets. This is the result on the public dataset. This result shows the effectiveness of TPS. Now let me talk about the second project, Intelligent Virtual Machine Pre-Provisioning. VM pre-provisioning is a system management process that creates a new VM on a physical host server and allocates computing resources to support the VM. The computing resources typically include CPU and memory, and it may also involve storage and network bandwidth. Provisioning is the most common and essential operation in Azure. Its performance, meaning how fast it is, directly impacts users' experiences. Therefore, the provisioning performance is one of the top metrics in Azure. To accelerate VM provisioning, a common practice is to get a pool of resources and pre-provision some VMs. This way, when a VM creation request comes in, if there's a match in the pre-provisioned VM pool, then this VM can be directly related to complete the rest of the provisioning process. Otherwise, the new VM has to be provisioned from scratch, resulting in longer provisioning time. As shown in this PPS process, the pre-provisioning algorithm plays a critical role because it decides how many VMs should be pre-provisioned for each VM type. Now, let's look closely at the VM pre-provisioning problem. There are two knowns and two unknowns. The size of the resource pool is known. It puts a constraint on pre-provisioning. The historical demands for each VM type are known. One unknown is the future demand for each VM type. The other is how to fit the future demands into the resource pool. Formally, given n time series as input, each representing the demand of a VM type from T0 to Tn-1, the output of the algorithm is the number of VMs to be provisioned at time t for each VM type. We formulate the problem as a prediction and optimization problem with the objective function to maximize the pre-provisioning hit rate and minimize the over-provision rate. Here, the hit rate means the percentage of the incoming VM provisioning requests fulfilled by the pre-provisioned VMs. Obviously, we want to maximize this metric. Over-provision rate means the percentage of pre-provisioned VMs that are not used. It is important to minimize the over-provision rate to achieve high efficiency on resource utilization. When we solve the problem, we should take the set of constraints on CPU, memory, storage, and network bandwidth into consideration. The VM pre-provisioning problem is quite challenging. First, there are huge numbers of VMs, and their demand patterns are very different. This makes the demand prediction extremely difficult. Second, prediction introduces uncertainty, which impacts the final result through optimization. How can we take this factor into consideration to achieve better result? Last but not least, the number of VMs for each VM type is discrete, and all the constraints are discrete, making this optimization problem NP-hard. We propose an uncertainty-aware framework for prediction and optimization to solve this problem. There are three components in this framework. In the prediction component, we use ensemble learning to address the challenge of predicting demands for a huge number of VM types with very different demand patterns. Please note that since this is a framework, other prediction methods can be used here. The prediction component outputs the predicted VM demand for each VM type and the corresponding prediction uncertainty. This is different from the existing two-stage approaches that only output the predicted demand to the optimization component. In the optimization component, we use a two-mode heuristic search approach to do the optimization. Here, two-mode means that we try to balance greediness and the randomness in order to avoid local minimum during optimization. Here, I want to point out that the optimization is conducted in the discrete domain without using any relaxation methods. This is different from the existing deep learning-based approaches that solve an approximate problem using relaxation. The third component is hyperparameter selection. It builds and maintains a surrogate model to continuously select the best set hyperparameters used in prediction and optimization. We compared our approach to the existing state-of-the-art approaches, including the two-stage ones and the deep learning ones. Our approach outperformed all of them. We worked very closely with our Azure partners and deployed this algorithm in production. While keeping the over-provision rate reasonable and stable, the hit rate is about 93%. The VM prevision time is reduced by about 42%. The results show that our algorithm is quite effective in production. Lastly, let me share some of our learnings and future research opportunities. The first learning is about data culture. Over the years, we have seen tremendous mindset shift towards the data-driven culture in both academia and industry, which is truly great. But we are not there yet. In practice, there are still many issues around data quality, including missing data, noisy data, delayed data, and low-value data, etc. This reality brings up interesting research opportunities around the instrumentation, how to make it effective and efficient. For example, where to log and what to log in the code, and how to evolve instrumentation. Around data quality management, how to conduct data quality testing, and how to continuously monitor the quality of data pipelines. The second learning is about proactive system design. Here is a high-level diagram illustrating this idea. The top part is a traditional system which monitors the input signals, gets the current status of the system, makes decision, and passes it to the action-taking component for execution. This traditional design is reactive, meaning it takes action only based on the current status of the system or the workload. In the design of a proactive system, a machine learning-based prediction component is added to the traditional system. The prediction system takes the input signals, does the necessary processing, and outputs the future status of the system or the workload. For example, what the capacity status of cluster A looks like next week, whether a disk will fail in a few days, or how many VMs of a particular type will be needed in the next hour, etc. The future status of the system and workload makes it possible for the decision component to take proactive actions to avoid negative impact on the system. For example, the service on an unhealthy computing node can be live migrated to a healthy one to reduce VM downtime. Another example is VM pre-provisioning we just talked about. Proactive system design brings up research opportunities. One is how to design the learning-based prediction components. The disk failure prediction project is an example. The second is how to design the new decision components when taking future status into consideration. The VM pre-provisioning project is an example. To summarize, today I talked about cloud intelligence, and I used 2 example projects to demonstrate our work in this research direction. I also shared future research opportunities in data quality and proactive system design. At Microsoft Research, we look forward to working with more and more researchers and practitioners from both academia and industry on cloud intelligence and making real-world impact. Thank you.